Hey, what's up guys? Welcome back to another video in the Tensorflow deep learning series. Now I'm going to teach you guys how to make a linear regression model using gradient descent, but with Tensorflow. That way we can get some good practice working with tensors and variables, and also automatic differentiation. I assume that if you're watching this video, you know what linear regression is. It's a way of essentially training a model to represent a line, a best fit line of some sort of linear data set. What I'll be using for this is the California housing data set, which is a very popular data set that basically tells you the value of a house based on a bunch of data points. So let me go ahead and start this up. Yeah, so the target is the median house value, and we have all these different metrics, these features here, like the median income, house age, average rooms, average bedrooms, population, latitude, longitude, all kinds of interesting things. And not all of these are going to be relevant for training a linear regression model, but the whole point of the video is how to train a linear regression model, but using TensorFlow, okay? If you want a detailed video on what linear regression is and how to code it from scratch completely, then watch my videos on that. I have machine learning videos specifically on linear regression, so make sure to check that out, okay? So anyways, this will use sklearn, scikit-learn to bring in the California housing dataset and put it into a data frame and extract the target from it and print out the head of the dataset. So the first five samples. Now we're going to split it up into the X matrix and the Y target value. That's usually what you do. So the X matrix is all the features of the data set. The Y is going to be the target vector. So it's a vector of all the actual targets for each of the samples. And then once you do that, you can usually split that into a training set and a test set. So we're going to do a test size of 20%. So 80% of this will be our training data, and then the other 20% will be used afterwards to test the model and see how accurate it is, essentially, okay? Now we're going to do feature scaling. So this will bring in the sklearn standard scaler to feature scale this data set because as we can see above, all of the columns here have different ranges of values. Some of them are very small, some of them are very large. For example, the population one gets pretty large. So we want to scale all of these to the same value while also retaining their meaning. And we can use the standard scaler for that, okay? So this will fit the scaler onto the training data and then, scale the training data, and then it will apply it on the test data as well. After we scale the data, we're now going to add a column of ones to the feature matrix, which will represent the bias term. And the reason is because we have our formula, which is y predicted is equal to theta times x, or the dot product of those two matrices. X is going to be our input, right? But theta is going to be our model parameter, so this is going to include our bias term as well as all of the feature weights. So since we have 1, 2, 3, 4, 5, 6, 7, 8 features, there's going to be 8 feature weights and then 1 bias term, and that's going to make up our theta. So that's going to be 9 total model parameters that we need to train a model to find, essentially. And then for that bias term, we want to have a column of ones because that's not included in the data set. So I think this helps visualize it a little bit better. So we have y is equal to x times theta. So we're simply doing the multiplication of the x matrix, which is our input values, all the samples in our data set that we're trying to feed into the model. And then we have theta, which is our model parameters. So that includes our bias term, along with all the model weights for each feature. So if we have one sample, this is what it looks like. We simply have a matrix here with one row. For the first column, you want to have a 1 because you need something to multiply against this first value here, which is our bias term value, okay? If you don't have it, then you can't really do the math to multiply these together. And then the second term here is the actual feature value. So this will multiply against this one here, which is our first feature weight. So if we increase the number of samples to, let's say, 2, this is what it looks like. Again, the only reason we have these ones here is because we need something to multiply against our bias term value, okay? So if we just increase the number of features, you can see that we always have that 1 there as the first column because we'll always have a bias term. And then for every single feature added, of course, that's more columns in our X matrix, but that's also more values in our theta as well because we need more weights for our model, okay? So this is what it looks like. This is just what we're calculating in terms of the math involved. Hopefully this visualization helps a little bit. You're simply doing a matrix multiplication between x and theta as a column vector, all right? So now we can actually do the fun part, which is implementing gradient descent using TensorFlow. So we're going to do import TensorFlow as TF, and we'll do define gradient descent, and we're going to pass in x, pass in y, we're going to pass in a learning rate, and then we'll do epochs as well, which is the number of times we're going to loop when doing the training process. The first step when doing gradient descent is to define your theta and give it random values, and those values will be obviously tuned to whatever minimizes our loss. So we'll do tf.variable, And the reason we're doing a variable versus just a regular tensor is because the theta is the thing that's going to be changing in this, right? So theta is not a constant, and tensors are constants, so you need to have a variable instead of just a regular tensor because it's going to be changing, okay? And not only that, when we use a variable, we can do automatic differentiation as we learned about before. So obviously we're going to need that. So to this, we're going to do tf.random.uniform. We're going to generate a random set of values, like I said. So we want you to find the shape of the tensor that is going to be generated from this. As we saw in our visualization just a second ago, we want the shape of our theta to be dependent on how many features we have plus a bias term. So we can go ahead and hard code it to whatever that value that would be, or we can dynamically grab it from X. So our X matrix will tell us directly how many columns we have. So we can do X dot shape and then just grab the second one, the first index, the second one, which is the number of columns in the X matrix. And then we're going to add another dimension to this random tensor that we're generating because we want this to be a vector, yes, for theta, but technically we want it to be a matrix vector, or otherwise known as a column vector, which allows us to do our matrix multiplication. Now we can also specify the minimum value of this random set of values that we're generating. So min value is equal to negative 1.0. Then we can do max value is equal to 1.0. And then the last thing that we're going to do, which is very important, is the d type, the data type, which we'll specify as float32. Like I told you guys before, in machine learning and deep learning, you want to have floating point values. All right, so we've generated our theta with random values, right? So now what we also want to do is basically replace x with a tensor. So we're going to do tf.constant and pass in x, and then change the data type of the data that's passed in by doing dtype is equal to tf.float32. Because we don't really necessarily know what data types are being passed in. It could be whole numbers like in32, it could be float32 already, but we just want to make sure that when we convert our x input matrix to a tensor matrix, that is definitely going to be floating point values because of the same reason I told you about. So then we can do the same thing for y. So y is equal to tf.constant, and then we'll do y dtype is equal to float32. Oops, tf.float32 like that. And then we also want to do y is equal to tf.reshape, and we want to reshape y to the shape by doing -1 and 1. And if you remember before, what this will do is basically take a vector and reshape it to a column vector, similar to what we're doing up here, to make sure that we can multiply it more easily. We can just go ahead and print this out to visualize what it's doing here. So we can do print y.shape, and then we'll do it again after. So print y.shape. Our learning rate we'll do, let's just say 0.01, that's a standard value. And then we'll epochs as 100. Or we'll do 10 to start with, okay? So let's go ahead and try this out. I made a mistake here. So instead of max value, it should just be max val. So that fixes that. Okay, here we can see that before it was a rank 1 tensor with 1 dimension, but then it has like roughly 16,000 actual values in that tensor. But then we're reshaping it to a rank 2 tensor, so that's basically a column vector or a matrix with 1 column and then 16,000 rows. Okay, so now that we have everything translated to tensors because we're doing TensorFlow, now we can actually do the calculations for gradient descent. So we're going to make a for loop here, so for in range of epochs. So the epochs will specify how many times we're going to loop in the training process here. And now the first thing that we want to do is calculate our predictions. So we're going to do y predictions is equal to tf.mat_mul for matrix multiply. And then we're just going to pass in the things that we're trying to multiply, which is our x and our theta. So we're going to multiply together our input and theta, which is our model parameters, and then get a set of predictions. And we're going to use this set of predictions to then evaluate how far off the model is from the actual values that we passed in. So that would be our loss. So loss is equal to tf.reduce mean, and then we'll do tf.square. And then inside of this, we'll just subtract our predictions from y. All this is doing is calculating the mean squared error, which is the loss function commonly used with linear regression. And this, again, helps us evaluate how far off our predictions are from the actual, okay? Now, at this point, what you would normally do is take your loss value and calculate the partial derivatives of the loss with regard to every single model parameter that you have in your theta. And it's not too hard to do that, but the cool thing about TensorFlow is that we learned that it's able to do that all automatically for us, which is really cool. So it'll give us the gradient directly. So we're going to do Control X, and we're going to replace this with tf.gradient tape as tape. Then we're going to put it back. So now all the calculations that we just did will be recorded in the gradient tape. So then once we're done here, we can now do gradient is equal to tape dot gradient. Now we just got to tell it what we're calculating the gradient for, so the loss and theta. So this will return the gradient, which is a vector with every single partial derivative of the loss with regard to every single model parameter in our theta. And what this will do is basically give us an indication of how changing these model parameters affects the loss. So it'll allow us to gauge whether we need to increase or decrease these different parameters, okay? And so we could do that by doing theta dot assign sub. So we're just simply subtracting the current values inside of theta, and we're going to subtract it by our learning rate times our gradient. So our learning rate allows us to basically control how far we step when doing this gradient descent process. So the lower this number is, the less you're going to be stepping each iteration, and then the higher it is, the more you're going to step. And so you want to find that sweet spot. So doing this multiplication here will give you the amount that you're going to step, and so you're simply going to subtract that from the current theta to update the model parameters. And you're just going to repeat this process for every single number of epochs that you have. So again, you're just going to calculate your predictions using x and your theta, calculate the loss to see how far off we are, calculate the gradient of the loss with respect to our theta to see how we need to change our theta, and that's it. We just repeat that process over and over and over until we run out of epochs. So then at the very end, what we can do is return theta. So this hopefully should be our optimized theta values, and it should give us hopefully a model that is able to understand our data set pretty well. So what I'll do now is just do theta is equal to that. And then I'm going to change the number of epochs to 100, so we let it run for a little bit and see how it performs. So let's run it now, and boom, it was really, really fast. Thing is though, as cool as this is, it doesn't really tell us much about how the model is performing. So there's different things you can do to gauge that. We'll learn a lot more about that when we actually jump into neural networks. But for this example here, one thing that we can do is just track our loss every single iteration. So we can add a list here, so training loss, and then every time we calculate the loss, we'll just add to that list. So we'll do training loss dot append loss, and then now we can return that along with our theta. So training loss, copy that, boom, and then let's rerun this again. So now we have both our values here. What we can do with that training loss list is actually plot it to see how it changes over time, so we can visualize that. So we can do it with this piece of code here. So we're importing matplotlib, and then we're plotting our training loss. The x is the epochs, and the y is going to be the mean squared error, which is our loss. And let's see, gradient descent is working because the whole point of gradient descent is to minimize the loss over time. So we can increase the number of epochs to, let's say, 1,000, and let's see what that looks like. So we can see around epoch 100, it starts to really slow down a lot and starts to plateau, but then by like 150, it's definitely just completely almost flatline from there. So we're not really improving our loss at that point. And then finally, one more thing that we can do is evaluate our model on our test data. I'll just copy that code. So what we're doing here is we're converting our x test to a tensor, our y test to a tensor, reshaping it as we did before. And then we're doing the matrix multiplication between our x tensor and our theta with the optimized theta values that we just calculated using gradient descent. That will give us our set of predictions. And then we're going to calculate the mean squared error on those predictions to see how far off they are from the actual. And then another metric that you can do usually is the R2 score. And here we go. So we get 0.55 and 0.57. These values don't really mean too much. Obviously, you can tweak your model to get better performance, but the whole point of this episode was to show you guys how to actually use TensorFlow at a low level so you can see how useful it is. So you learn how to use variables and tensors, but the real big part of this is using the gradient tape. The automatic differentiation part is really, really important for deep learning. So the whole point of this episode was to show you that. And I know this is a deep learning series, and we just made a machine learning model, just a standard machine learning model, not a deep learning model. But I think actually showing you TensorFlow in action is really, really important. So hopefully you found this pretty useful. So that's it for this video, everybody. I really hope you learned something new. If you liked the video, please hit the like button, and if you want to see more, hit that subscribe button. Make sure to also check the description below for important links to code and other resources, but also really important, join our Discord. We have a big community of over 5,000 programmers, and it's a place where you can find new friends or get help on any code that you're stuck on. If you want to support what I do on this channel, please consider hitting the join button below, and this will allow you to support my channel for as low as $1 a month, but there are different tiers to choose from if you want to. For anyone that becomes a member on my channel, you get a special rank on my Discord server, early access to new videos, and you can just see yourself on the screen right now. So if that sounds cool to you, feel free to join. If you don't want to, that's fine. If you can't, that's okay too. I really just appreciate you watching the video anyway. Thank you so much. And that's it. Peace.